Alright, we're going to start the Chapter 9 Homework A review. This is the penultimate homework review for this semester and also the last material that you'll be responsible for on the third exam that's coming up this week for all of you. Alright, so we're going to go through several questions here that either we had a 50% success rate or less, or in a couple cases were suggested by students, and they're also good ones to go over as well. So we're going to go through about 12 or so questions here, I think, and the other thing to keep in mind is if you have any additional problems you want to go over with me, I will be in my office tomorrow afternoon, or I'm available online for appointments as well, so definitely get things cleaned up on this assignment, because it is, again, going to be at least a part of our exam coming up. So the major topics in this part of the chapter, the first half of Chapter 9, are properties of liquids and phase changes. So those are the two things that we're going to cover throughout this review. All right, so the first thing we want to talk about are, in one of the first major topic of Chapter 9, are intermolecular forces, which are forces of attraction between two or more molecules in a condensed phase, particularly in a liquid or a solid. So this first question here actually asks us to really distinguish between inter and intramolecular forces, and the answer that many of you picked was showing that you were not still quite clear on the distinction. So here we're talking about the bonds between hydrogen and oxygen within a water molecule. So again, within means a single water molecule, and what can these be characterized as? All right, so to give us an idea of what we're talking about here, we have a water molecule, which is H2O, which we know by now is a bent molecule. And what we're talking about is how would we classify these bonds here between O and H within a water molecule. Now, we learned back in Chapter 3 that would be called a covalent bond. It's two nonmetals bonded to each other. It's polar because of the great electronegativity of oxygen. But this is a force that holds this single water molecule together. So this type of force, which is a covalent bond, it's not in the answer choices, but that would be more generally classified as an intramolecular force. So you have to remember that in this case, intra means within, and inter means between. So many people on this question either picked choice C, which is intermolecular, or choice A, which is a specific type of intermolecular force, hydrogen bonds. But again, that's only when we're talking about forces between two or more water molecules. So if we were showing what a hydrogen bond looked like, it would be something like this, where we have one water molecule, and then we have another one that sort of lines up next to it. And you have your partial minus here, partial positives on hydrogen. So if you have a partial negative and a partial positive next to each other, you have this strong dipole force. And this interaction between two different water molecules, this would be called a hydrogen bond, or more generally an intermolecular force, okay? So this problem asks us to make sure we understood that distinction between intra and intermolecular force. And the bonds between atoms in a molecule are always going to be classified as intramolecular. Within that molecule holding the single molecule together, intermolecular forces always involve forces of attraction between two molecules or more than two molecules if you have a condensed phase. All right, so with that out of the way, now we're going to start talking about how to classify the intermolecular forces and predict which ones will exist. So this question asks for the strongest intermolecular reactions between hydrogen sulfide molecules, and what do they arise from? Now, the first thing we can do is we can look at the answer choices and probably eliminate a couple, because if we're talking about a covalent compound, hydrogen sulfide is covalent, it's two nonmetals, hydrogen and sulfur, we can say there's only going to be three possible intermolecular forces. It's going to be either dipole forces is one of them, London dispersion forces, hydrogen bonding. Those are the only three types of intermolecular actions you can have. In other types of solid materials we talked about, we have metallic bonding, ionic bonding. Those are more like those are kind of in between intermolecular and intramolecular. I wouldn't really classify them in this way anyway. But we're talking about here just a simple covalent molecule. Those are the only three possibilities. So ion-dipole interactions, that's not going to come into play because we don't have any ions involved in this compound. It's covalent. And then disulfide linkages, this is something you would learn probably in a biochemistry setting, has no relevance to intermolecular forces in this context. So our answer choice is going to be one of these three, looking for the strongest ones. And so the other one that we can easily eliminate is hydrogen bonding, because hydrogen bonding forces, we mentioned them a little bit in the last problem, but when do they occur? They require hydrogen being bonded to oxygen, fluorine, or nitrogen, one of those three electronegative elements. So those last three 2p elements. So this requires hydrogen bonding being bonded one of those. Now again, that bond itself is not the hydrogen bond, but when you have hydrogen bonded to one of these elements, then you would have hydrogen bonding between the molecules of that compound. So we can eliminate choice C also, because choice C is again only going to exist in these specific cases. So now you have to decide, is this molecule going to have London dispersion forces as the strongest force, or dipole-dipole forces, and that is going to come down to whether or not the molecule is polar. So when distinguishing between these two, London dispersion forces will be the strongest forces in a nonpolar molecule, and then dipole-dipole forces will be the strongest force in any polar molecule. So you have to decide if H2S is polar or nonpolar. Now if we go to the periodic table quickly, we can see that we know, and we should remember also, that sulfur is right below oxygen in the periodic table. So H2S is going to be the same structure as H2O, just with sulfur at the center instead of oxygen. So we don't have to go through all the steps. H2S is going to look like this. So again, if we want to talk about things in AXE notation as a review of that, but whatever the case is, we realize that this molecule is bent, and all bent molecules are polar. Okay, so this one's polar, which means it will have dipole-dipole forces as the strongest forces, and that's going to be choice A, because dipole-dipole forces are stronger than London dispersion forces. It will also have London dispersion forces, not that they don't exist, but the dipole-dipole forces are stronger, and that's what this problem wanted us to identify. All right, and then we're going to go on to a couple of problems that deal with the properties of liquids and how they relate to intermolecular forces. Now, in general, almost every property of a liquid increases with the intermolecular forces. So, viscosity, surface tension, boiling point, those are the three major ones, I suppose, but they all increase with temperature. Or sorry, not with temperature, but with intermolecular forces. So the stronger the intermolecular forces, you're going to have higher viscosity, higher surface tension, higher boiling point, all that stuff, okay? Now the only one that doesn't increase with intermolecular forces is vapor pressure. This is another major property of liquid. It doesn't come up on this problem, but it will come up a little bit later. But vapor pressure is going to decrease with stronger intermolecular forces. And that should hopefully make sense conceptually, because intermolecular forces are telling you how strong are the molecules held together. If they're held together more strongly, less of them are going to escape in the vapor phase. But here, this problem deals with viscosity, so if we're looking for the greatest viscosity, we're looking for the molecule that has the strongest intermolecular forces. So again, we have to classify what is the strongest intermolecular force in these 5 choices, pick the strongest overall. In some cases, we might have to compare two molecules that would have the same intermolecular forces and figure out which one is stronger of those. So that's how we're going to do this one. All right, so choice A is a hydrocarbon hexane, C9HW A, only has carbon and hydrogen in the formula. And what's helpful to remember for molecules like that is because carbon tends to form 4 bonds, it has no lone pairs involved, these hydrocarbon molecules, whatever their formula is, are going to be nonpolar. So choice A, hexane, is nonpolar, so it's only going to have dispersion forces as its strongest intermolecular force. Alright, that's going to be helpful for this part of the course. If you see a hydrocarbon, something with just carbon and hydrogen, remember that it's nonpolar, and that's only going to have dispersion forces as a result. Now for the next two, B and C, we have to sort of draw out the structures to some extent. But again, we have in the middle of these formulas oxygen atoms. We know that oxygen tends to have 2 bonds and 2 lone pairs, so these are both going to be bent molecules. So I'll draw the one from B first, quickly. So we'll have an oxygen, which is going to have sort of 2 carbon chains coming off of it at different lengths here. And then C would look similar. It's going to be, this time, 2 identical carbon chains coming off. But in either case, Again, oxygen tends to be 2 bonds and 2 lone pairs, which makes it bent. The carbon-oxygen bonds are polar, so these are both going to be polar molecules, but they don't have any hydrogen atoms bonded directly to oxygen. So they're not going to have hydrogen bonding interactions because all the hydrogen atoms in these structures are bonded to carbon, not to oxygen. So these will be polar molecules. They'll have dipole-dipole forces, but not hydrogen bonds. So choices B and C, that's going to be the strongest intermolecular forces present. And then for D and E, we see in both cases we have an OH, one or more OH groups. So again, that indicates that hydrogen is bonded directly to oxygen. In that case, you're going to have hydrogen bonding as the strongest intermolecular force. So it's going to be between choice D and E because choices D and E are the only two that have hydrogen bonding interactions. Hydrogen bonding is the strongest type of intermolecular force. So with hydrogen bonding, you would expect the viscosity to be the greatest. Now the question is, comparing D and E, we have to figure out which one of those is stronger. So in choice D, we have just one hydrogen bonding site. Again, the OH bond itself is not the hydrogen bond. I want to emphasize that. But we have one hydrogen bonding site in choice D, but in choice E, we have two. We have an OH there and an OH there. So even though these molecules have similar size, similar molar mass and all that, choice E, you have two hydrogen bonding sites. That makes the molecule able to form more hydrogen bonds when they're condensed together in a liquid. That will lead to overall stronger intermolecular forces and higher viscosity. So choice E is going to be the correct one here because it has the strongest type of intermolecular force and it has more of those possibilities than the one above it. Alright, so when we're talking about different liquid properties, it's going to usually come down again to comparing intermolecular forces to be able to figure out which liquid has the greatest value for a certain property. In this case, it was viscosity. And then this one is very similar. We're talking about surface tension here. Now, I think what happened in a lot of this problem here was a lot of people failing to identify which molecules were polar or nonpolar. I think this is a typo here. This should be CH4. That's my fault. So that first one should be CH4 liquid. Then we have CF4, CCl4, CBr4, and CH3Cl. Now, so a lot of people picked choice D here, and I think what they were doing was they were assuming that all of these molecules were nonpolar, and then they were choosing the one that has the largest molar mass, which would be true if they were all nonpolar. Again, we have to think about whether or not they're nonpolar or polar first. None of these will have hydrogen bonding interactions because the only one that even has hydrogens are A and E, and in both cases they're bonded to carbon and not bonded to nitrogen, oxygen, and fluorine. So hydrogen bonding is out, but we have to identify then for these molecules, are they polar or nonpolar? Polar molecules would have the stronger dipole-dipole forces, which make them have higher surface tension, versus nonpolar molecules, which would have just the London dispersion forces and then expect to have weaker surface tension. Alright, so let's go through these choices here. So for A through D, all of these are going to be CX4 molecules, where X is the outer atom. And so in a CX4 molecule, as we should know pretty easily by now from all the stuff we've done back in chapter 4, carbon tends to form 4 bonds and have 0 lone pairs to complete its octet. So this will be tetrahedral AX4, but because there's no lone pairs on the central atom and because all of the outer atoms are the same, these would all be nonpolar. So all of these first 4 answer choices here, A through D, are going to be nonpolar. So that means they're only going to have London dispersion forces. So if we were comparing A through D, we'd have to figure out which one has the strongest London dispersion forces, which would be the heaviest one, the one that has the most electrons, which makes it the most polarizable. And so for choice A through D, D would be the highest surface tension. But we have to consider choice E as well, and as I'm kind of hinting at now, choice E is the one that's a little bit different from the rest. So in this case, it's still, in some sense, an AX4 molecule, but this time it has 2 different outer atoms. You can call it X3, X prime. 2 different outer atoms can be written in this way. And so in this structure here, it's still going to be tetrahedral, but now it has 2 different types of outer atoms, hydrogen and chlorine. Let's put the chlorine at the top to make it a little bit easier to see. But something we talked about a little bit in chapter 4, it didn't come up as often, but it was still something we mentioned, is if you have a tetrahedral molecule with two different outer atoms, whether it's one of 1 and 3 as we have here, or 2 and 2, which is the other possibility. In this case, it's going to still be tetrahedral. That doesn't change the structure. But it will be polar because we don't have all of the same bond dipoles. We have four bonds total, but 3 of them are different than the other one. And so the bond dipoles are not all the same, so they don't cancel out in this case. So any tetrahedral molecule that has two or more different outer atoms, in this case 3 hydrogens and 1 chlorine, or even if it was 2 of each, 2 hydrogens, 2 chlorines, in that case you're going to have the molecule being polar. Alright, and so because choice E is polar, it has dipole-dipole forces. And dipole-dipole forces are stronger than London dispersion forces. And so we would expect then that would have the highest surface tension because it has the strongest intermolecular forces. So that's going to be choice E then that we would pick because, again, of its polarity. In this case, it's the only one in this choice of these choices that's polar. So many of you, I think, fail to recognize that choice E is polar, but if you have two different outer atoms in a tetrahedron, then it will be polar. All right. Now these next two questions, one of which was a suggestion from a student, deals with a concept that we didn't exactly talk about a lot in class. I think I may have mentioned the word, but didn't define it clearly necessarily. But it is still related to intermolecular forces, and most specifically, this term here, polarizability, is related to the strength of London dispersion forces. But basically, polarizability, as sort of a quick definition, is the ability of the electron cloud to distort. So in these two problems here, we're trying to compare the polarizability of a bunch of atoms. And so for a single atom, the greatest or the largest polarizability means it has the largest atomic radius. And the reason for that is we're looking for, if you want to talk about the ability of an electron cloud to distort, we're looking for the one where those outermost electrons, the ones that are furthest away from the nucleus, and that sort of determine all the chemistry for that atom. We're looking for the atom where those valence electrons are held the least strongly, the loosest held valence electrons, allowing them to distort. And so that's going to be the one that has the largest radius, because in that case, the outer electrons are furthest away from the nucleus, they're not held as tightly, and they're better able to distort. So when you're asking a question like this that deals with polarizability of a single atom, all we need to look at is the atomic radius. And the one that has, in this case, we're looking for the smallest polarizability, should be the one that has the smallest atomic radius. So we have silicon, sulfur, tellurium, bismuth, and bromine. So let's go find those in the periodic table and compare their radius. See if I remember all that. But anyway, remember that atomic radius is going to be, if we're looking for the smallest atomic radius, we're looking for the one that's going to be furthest to the right and furthest up. So radius is going to decrease left to right and bottom to the top. So we have silicon, sulfur, bismuth, tellurium, and bromine, I believe. So bismuth is row 6, it's pretty far down. Tellurium is above that, so that would be a little bit smaller. Bromine is above that, so it's a little bit smaller. But now if we go up an entire row of the periodic table, that's the last two, silicon and sulfur. We expect those two to be the smallest. So anytime you move up a row in the periodic table, the radius does tend to shrink. So if we go from bromine up to here, for silicon and sulfur, those are going to be smaller. And then between those two, as we move left to right, we're going to get smaller. So sulfur will be the smallest of all these answer choices. Alright, so sulfur has the smallest radius. Again, the effect of going up an entire row of the periodic table tends to be bigger than the effect of moving left to right. This one, these three here are all in lower rows of the periodic table. Silicon and sulfur are in the same row, third row of the periodic table. Sulfur is to the right, so it would be the smallest and the least polarizable. The next question is basically the exact same concept, so I'll go ahead and just do it. Again, now here though we're looking for greatest polarizability, which means you want the largest atomic radius. With the largest atomic radius, the electrons will be furthest away from the nucleus, and they'll be better able to distort. So we have fluorine, bromine, polonium, lead and helium, and we're looking for this time the biggest radius of those ones. So if we go to those ones, helium is very small, of course. Fluorine is pretty small as well, bromine, and then we have lead and polonium, Pb and Po. So these are going to be the ones that are in the lowest row of the periodic table, so those ones would be expected to have the largest radius compared to the rest, which are all above them. But again, if we're looking for the biggest radius, we want furthest down and furthest to the left, so we expect lead here to be bigger than polonium because it's to the left. As we go right to left, we increase the radius. So lead should be the biggest of those, and then also the most polarizable. Alright, so even though this sounds like a totally new concept, it really just comes down to atomic radius when we're talking about the polarizability of a single atom. For molecules, it's a little bit more complicated. It mainly deals with how many electrons or the molar mass of the molecule, but also a little bit of the shape. So polarizability for molecules is a slightly different comparison, but for a single atom, it just comes down to atomic radius. All right, now we're going to deal with some questions. One question that deals with a more quantitative aspect of vapor pressure. So this was a request from a student in the course. And we're trying here, in this case, to calculate how much water would be in the gas phase when it establishes an equilibrium between liquid and vapor. So we have 75 degrees Celsius sample of water, and we know the equilibrium vapor pressure is 289.1. So that means when you have water at 75 degrees Celsius, if it's in a closed container, it's going to, the water is going to evaporate until it gets to a pressure of this value here. So if we put 4.22 grams of water in a 5-liter flask and heat it to 75 Celsius, what mass of water will be found in the gas phase when the liquid-vapor equilibrium is established? Now, this problem here may have sounded like something totally different than we've seen before. Well, how do we calculate mass of water in the gas phase? We can cover that in class, but in reality, it's just an ideal gas problem, much like Chapter 8. So what we're going to do here is, again, we're going to allow water to evaporate into the gas phase. So we have a closed container of water, a little bit of water at the bottom, and then we're going to have some water that escapes into the gas phase. And we know the pressure of that water vapor, we know the volume of the container, and we know the temperature. So just like we did in Chapter 8, let's calculate how much water vapor, how much gas that it corresponds to by using PV equals nRT. And, water vapor is not exactly an ideal gas, but it's going to be, this equation will still work pretty well, and we can use it to figure out how many moles of water are in the gas phase and then calculate the mass. So we're going to start by calculating the moles of water, which is PV divided by RT. In order for this to work, because we're using R, we need to have our vapor pressure be in atmospheres. So the vapor pressure in this case, which is 289.1 millimeters of mercury, we have to divide that by 760 to get it in atmospheres. Alright, so we're going to divide that by 760. So it's 0.3804. Keep 4 sig-figs just don't round too much. 0.3804 atmospheres is our vapor pressure of water at that temperature. The volume of the flask is 5 liters, so the water vapor will be distributed throughout that whole volume. R is the universal gas constant, which is on our periodic table if you forget it. 0.0821 liter atmospheres per K mole. And then the temperature in this case is 75 Celsius. That needs to be in Kelvin, so we'll add 273 to that and get 348 Kelvin. Alright, so this is going to allow us to calculate then how much water in terms of moles is in the gas phase at when you get to that equilibrium vapor pressure. So give me 1 second to get that number. Alright, so I got 0.00, sorry, just 10, 0.6657. Alright, and then what we're going to do is we're going to calculate the grams of water in the gas phase, which is what this is asking for. So we're going to take that amount of water in moles, and use the molar mass of water, which is 18.02 grams per mole. So when we multiply that by 18.02, we'll get the mass of water in the gas phase, which is 1.20 grams. I think this is a multiple choice question, and that was one of the choices there. Now, the only other thing to talk about in this problem, so that's it for this one. We can calculate the mass, and we're good to go. The only other thing to talk about is what if this number here was larger than the amount of water we had put in. So let's say instead of putting in 4.22 grams of water, we only put 1.0 grams of water, but then we calculate that you'd have 1.20 grams in the gas phase. So in that situation, if you put in less water than this amount, that would mean that all of the water that you put in evaporates and goes into the gas phase. You don't have really an equilibrium between liquid and vapor in that case because the vapor pressure is higher than the amount of water that can evaporate. And so in that case, all the water would evaporate. So if we had put in anything less than 1.20 grams into this flask, all of the water would have evaporated and we would have not quite got up to the equilibrium vapor pressure. But in this case, we have more than enough water, so we're going to evaporate water until we get to 289.1 millimeters of mercury. We'll have some water. The rest of that, about 3 grams, will still be in the liquid phase, but 1.2 grams will be in the gas phase. And again, we calculate that amount just using the ideal gas equation. All right, so that takes care of that one. Now the next few questions are really the only type of quantitative problem we had in this chapter. Though I guess that last one is fairly quantitative too. But in general, the major sort of new quantitative concept we introduced was calculating heats involving phase changes or combined with heat terms that involve raising the temperature. And we didn't do particularly well on these questions. These were questions that had variable numbers, so you might have gotten different numbers in your problem, but the steps were the same. But probably the challenge in these types of problems is knowing which steps are relevant. So you really have to think about the situation you're in, what temperature you're starting at, what temperature you're ending at, and try to consider which phase changes you go through. Because in problems like this, there's two possible processes to consider. You have to worry about a phase change, or you have to worry about a temperature change. Both things can possibly be at play here. So what we're asking here is if we have 3.75 gram sample of ice at this initial temperature, what is the minimum amount of heat needed to convert the sample to ice at 0 degrees Celsius? So the first thing we have to think about is for water, this is ice, which is just frozen water, where do the phase changes occur? So the phase changes, you're going to go from ice or solid to liquid at 0 degrees Celsius, and then you're going to go from liquid to vapor, boiling it at 100 degrees Celsius. So for water, we do need to know which temperature those phase changes occurred to be able to do problems like this. In this problem here, we're starting with ice is below the melting point, so it's going to be solid ice in this case. And the minimum amount of heat needed to convert the sample to ice at 0 degrees Celsius. So here we're not actually doing the phase change. We're going to the phase change temperature. We're going from minus 52.6 to 0, but we're remaining at ice. It's still, again, look at the wording of the problem. It's still ice at that temperature. We haven't gone through the phase change yet. So we're just calculating the amount of heat needed to warm the sample from minus 52.6 to 0 degrees Celsius. No phase change involved. It's still ice before, it's still ice afterwards. No phase change. So whenever you're doing a temperature change without changing the phase, it's just going to be MC delta T. So in problems like this, we always give you a lot of information. We give you two specific heat capacities, two different phase change enthalpies. But for these problems, you don't necessarily need to use all of the information. And so for this problem here, we're just doing a temperature change. We're not doing a phase change. So it's just going to be MC delta T. We just have to make sure we use the correct heat capacity because here, again, we're dealing with ice. So we need to use the specific heat capacity for ice, not for liquid water. So that's going to be this one there. So from there, all we have to do is just plug in the numbers to get this. So we have 3.75 grams of ice. The heat capacity of ice is 2.10. We have to make sure we use, again, the correct value for that phase that we're in, which is solid. And then delta T, we're going from minus 52.6 to 0, so the delta T is positive 52.6 degrees Celsius. And so when we multiply that out, I think we're looking for this answer in kilojoules, so we'll have to divide by 1,000 at the end. So we get 414 joules, which in the correct unit would be 0.414 kilojoules. Alright, so that's how much heat is required to raise the temperature of the ice from minus 52.6 to 0, and that's all we're doing here. We're staying at ice, so we're not doing a phase change. We're not involving liquid water at all. We're staying in the solid phase. So that was one variation on this problem that you got. And then here's another one that's, again, looks almost the same. And I kept the numbers the same just so we didn't have to do as much work to solve it here. But again, still 3.75 gram sample of ice, still at minus 52.6 degrees Celsius. But this time we want to know what is the minimum amount of heat needed to convert the sample to liquid water at 0 degrees Celsius. So in this problem here, we're doing two stages. Stage 1 is going to be the same as the last one. We're warming the ice from the starting temperature to the phase change temperature of 0.0 to 0 degrees Celsius. In the last problem, that's all we did because we still stayed at ice. We didn't do the phase change. But then in this case, we also have a second stage, which is going to be to melt the ice. Because we're going, again, from ice to liquid water. When you go from solid to liquid, that's melting it, so you have to account for how much heat is also required to melt the substance. And then we add the two together. So for stage 1, it's just the exact same as the last problem. I use the same numbers on purpose. So Q, again, is MC delta T, and we're talking about just raising the temperature. And as we found in the last one, that comes out to 0.414 kilojoules. Those are the numbers from the very last problem I did. But then for stage 2, we have to use the correct phase change enthalpy to figure out the heat. And because we're melting here, the phase change enthalpy associated with melting is called the enthalpy of fusion. So we're going to use heat of fusion here for the second term. We'll notice here that heat of fusion is given in kilojoules per gram, so we just have to multiply the mass by the heat of fusion to figure out how many kilojoules that would be. So a lot of times these phase change enthalpies are going to be in terms of kilojoules per mole, so if you look at the units to figure out which quantity we use, but here it's directly given in kilojoules per gram, so we don't need to do any conversions for the amount of substance. So the heat for this term here is just going to be the mass times the delta H in kilojoules per gram, which is going to be 3.75 grams, and then the phase change enthalpy was 0.335 kilojoules per gram. So to make sure we're using the correct phase change enthalpy, and we're multiplying by the mass in this case because the phase change enthalpy is in per gram terms, and that comes out to 1.26 kilojoules. Here the answer is directly in kilojoules because that's the unit of our phase change enthalpy. And so then the total heat for this process would be the two added together, 0.414 kilojoules to warm the ice to the melting point, and then another 1.26 kilojoules to melt the ice. So again, we're doing both things here. When we add those together, I get maybe a little bit of rounding, but anyway, 1.67 kilojoules for this one. Alright, so that's the amount of heat needed to do both of those things. And then finally, this third one here is even slightly more complicated because here we're starting with 3.75 grams of ice at 0 degrees Celsius, and we want to know what is needed to convert the sample to liquid water at 18.7 degrees Celsius. So for this problem here, if you want to think about what we're going from ice, we're going to melt it to liquid water, and then we're going to warm it to 18.7 degrees Celsius, still liquid water. Alright, so we're not going past the next phase change. The next phase change for liquid water would occur at 100 degrees Celsius, so we're not going there. But here we're starting with ice at 0 degrees Celsius, so it's solid at the beginning, and then at 0 degrees Celsius we're going to melt it to liquid. That's the first step. So again, let's keep those straight here. So in this problem, stage 1 is going to be to melt the ice, because we're already at the phase change temperature, so we don't have to warm up the ice at all. It's already at 0 degrees Celsius, which is where it will melt. But we do have to melt the ice because it's starting out solid, and we're going to convert it to a liquid. And then stage 2 is going to be to warm the water. So once it's melted, it's in the form of liquid water, and we're going to warm it from the phase change temperature to the final temperature of 18.7 degrees Celsius. So for stage 1, the heat is going to be calculated exactly the same as the last problem. It's going to be mass times delta H, again because delta H is given per gram of substance here, and we're going to use the fusion enthalpy again because we're melting the ice. So that's going to be the same number as last time. So the second stage last time gave us 1.26 kilojoules. So as we found in the last problem, it takes 1.26 kilojoules to melt this much ice. So that's stage 1. And then stage 2 again is a situation where we're just warming the substance up. We're at liquid water once we melted it, and we're going from 0 degrees to 18.7. So that's just going to be Q equals MC delta T. Alright, so it's still 3.75 grams. But this time we need to use the specific heat for water because we're at liquid water now after we've melted it. So we're going to use the more familiar 4.184 value. And then delta T is going to be 18.7 degrees as final temperature, 0 degrees as initial, so the delta T would be positive 18.7 degrees Celsius. Alright, so again, you likely had different numbers than these in your problem, but in this case it's going to be this final step here. So that comes out to 293 joules, which is 0.293 kilojoules. And again, this is a two-stage process, so now we're going to add the two together to figure out the total amount of heat. 1.26 kilojoules to melt the ice, another 0.293 kilojoules to warm up the water to the final temperature. And so when we add those together, this time we get 1.55 kilojoules. All right. So that's how we're gonna approach these types of problems here. You have to figure out which processes are happening. Is it a phase change? Is it a temperature change? Is it both? And so there's different levels of complication. You're typically not going to use all of these information up here to figure out which ones are relevant. Specific heats are relevant when we're changing the temperature, and you can keep track of which phase you're changing the temperature of. And then these enthalpy values, or heat values as they're labeled here, fusion and vaporization, are going to be associated with the phase changes. So make sure you go over problems like this. It's the one major numerical problem type that we introduced in this chapter. And the math is not too difficult for both steps. You just have to figure out which steps are relevant to be able to do this correctly. All right, the last question here is really the only phase change problem that we had a little bit of trouble with. There were several, so make sure you go over those if you had them. And if there's any other questions on phase changes, or phase diagrams, I should say, let me know. So in a phase diagram, again, it's a temperature-pressure diagram. So it shows which conditions of temperature and pressure a certain substance exists at. Now this one doesn't even have numerical scales, so we can't really say anything quantitative about this one in terms of which temperatures or which pressures do phase changes occur at, but we can still say some qualitative things about that. So in this one here, we're talking about some unknown substance X. We know which of these will result in vaporization of X. So if we're considering vaporization, remember we have to remember the definition of vaporization. So vaporization is a phase change that involves converting the liquid to the gas forms. So we're looking for a situation here, we're talking about vaporization of X, where we're starting out as liquid X and converting it into gas phase. So it's helpful to label the phase diagram. Remember that in these diagrams are typically going to be three regions. The furthest to the left is solid, furthest to the right is gas, and in the middle is going to be liquid. Alright, so those are the three regions of the phase diagram. And for vaporization, we want to start out as a liquid and end up as a gas. So let's look at the different answer choices and go through them. So here, choice A, with conditions indicated by point A, so we're starting here as a solid. So we're not going to be doing vaporization because we're starting as a solid. So if we raise the temperature and pressure until it reaches H, A to H is going to be solid to liquid. So that would be a melting process because we're starting out as solid and going to liquid. So choice A would be representing melting, not vaporization. Here we're talking about conditions by point F. So point F is on the liquid-gas equilibrium line. Then we want to raise the temperature and pressure until it goes from H. So here again, at point F we have liquid and gas phases because we're at the borderline between them. When we go to point H, we're in liquid only. So this would be considered condensation because, again, we're starting with liquid and gas together and we're changing it completely into liquid. So we do have to know these definitions of it. But again, this is not vaporization because we're not going from liquid to gas. We're going from a mixture of the two back to pure liquid. With X at conditions point H, so here for choice C, we are starting in the liquid part of the diagram. Change the temperature and pressure until it reaches A. So for choice C here, we're going from H to A. This is liquid to solid. Liquid to solid is considered freezing the substance, so that's not going to be vaporization either. We need to find liquid to gas. For choice D, conditions indicated by point A, which is solid, lower the pressure to that of point C, and then raise the temperature. There might be a typo there. But anyway, in this problem, in this choice D, we're going from A to C. I think we're going sort of like this, is what it's sort of indicating. But again, the net process here for choice D is going to be solid to gas. When we go straight from solid to gas, that's called sublimation. I don't know if I have room to write that, but this is sublimation, not vaporization. So then the only choice that's left is E. And here for choice E, we're starting at H, and we're changing the temperature and pressure and going to C. So in this answer choice, we're going from H, which is in the liquid part of the diagram, to C, which is in the gas part of the diagram. This would in fact be vaporization, and so that's going to be the correct answer choice. So for this problem here, the two tricks were to make sure you know how to read phase diagrams, at least qualitatively, and then also that you know the different definitions for phase changes. So all of these processes involve a phase change because they're starting either with one phase and going to another, or starting with a mixture of two phases and converting it back to a single phase. So they all involve phase changes, but the only one that's vaporization is choice E, because that's the only one where we go from liquid to gas. All right, that takes me to the end of this week's review. We'll just have one more of these next week, to get ready for the final exam, the last part of Chapter 9. So if you have any remaining questions on this material, please get in contact with me, and best wishes on your exam this week, and I'll see you guys in class tomorrow.